I'm Amit Chandra Pathak, CSE AIML department, and the topic is AVL Tree. So, in today's lecture, we are going to learn about AVL Tree, a special type of binary search tree that keep itself balanced automatically. So, by the end of this video, you will understand what an AVL tree is, why balancing is important, and how rotation work, and how insertion and deletion maintain balance. So we start first slide. So what is AVL tree? So it was invented by Adelson Valensky and Landis, three scientists of Russia in 1962. So that's why it is called AVL tree. In a normal binary search tree, if we insert node in a sorted order, the tree become skewed. Right skewed tree, left skewed tree, or right skewed tree. So it behave like linked list in this case. So and searching takes means complexity is O n time. And but in AVL tree, after every insertion or deletion, the tree check its balance factor. Means the balance factor always should be 0, 1 or -1 on every node. So if we check the balance factor on every node and perform rotation if needed. So what is the rotation? Rotations are mainly four type: LL rotation, RR rotation, RL rotation, LR rotation. As needed, we use the rotations R. So AVL tree guarantees for the complexity is O log n time for search, insertion and deletion. It is better than O n time complexity. So here is the example of AVL tree. So here we go to the second slide. Example of binary search tree. This is not an AVL tree. So we can see this tree is not an AVL tree. Every node, the balancing factor is more than 1 or less than -1. So we have to notice that less than, or what is the mean of less than -1 or more than +1. If the balancing factor is less than -1, so always be a is will be a -2, and more than +1, so always be a +2. So it is not a balancing. Here we can say the over time while ensuring the overall time complexity remain O log and AVL tree, and also the four type of rotation. Now the slides go to the insertion deletion use case and drawback compared to other tree in order traverse. So you can see. So first we have to notice that how do we find the balancing factor. So simple formula is the balancing factor find is right left subtree minus right subtree. Always should be +1 -1 or 0. Now we can see the insertion and deletion. While insertion is followed by upward traversal, so check balance and apply rotation. Deletion can be more complex due to multiple rotation possible being required. AVL tree may require multiple rebalancing steps during deletion, unlike red black tree which limit this use case. Now so we have to consider this important point is use case. AVL tree are particularly useful when you need frequent and efficient lookups, like in database indexing, memory intensive application, or where predictable time complexity is crucial. Also, we have to discuss one drawback. Although faster in lookups than red black tree, AVL tree might cure slightly more overhead on insertion and deletion due to strict balancing requirement. As a result, red black tree are more common in standard library like tree map, tree set in Java, or map in C++. So another slide, operation on an AVL tree. So how can we or different type of operation we can do here. So searching, insertion, deletion. So first we discuss about searching. It is same as normal binary search tree. As an AVL tree is always a BST, so we can use the same implementation as a BST. The advantage here is time complexity is low in search. And insertion, very important, that if we insert any node, so always we have to manage that every node should have or must have the balancing factor 1, -1 or 0. It cannot be more than +1 or less than -1. If it show the balancing factor -2 or +2, that means it is not balancing, it is not balanced, and it is not AVL tree. So we have to use the whole type of rotation LL, RR, RL, LR to balance, to manage the balance here, to fix this imbalance. Now we have to discuss deletion. It is also same is, so if we delete any node, so always have to manage here the balancing factor. uh, Balancing factor we have discussed previously, -1, +1 or 0. Now the slide is rotating the subtree used in insertion and deletion. Yeah, we discuss here left rotation is very simply the LL rotation occur when a node is inserted into a left subtree of the left child, causing the balancing factor to become more than one. Fix, perform a single right rotation. The solution is, if need is the left rotation, so we perform a single right rotation occurs when a node is inserted into the right subtree of the right child, making the balance factor less than -1. So how do we fix this problem? So perform a single left rotation here. Now left right rotation occur when a node is inserted into the right subtree of left child, which disturb the balance factor of an ancestor node, making it left heavy. So how do we fix this problem? Perform a left rotation on the left child followed by the right rotation on the node. Now right left rotation occur when a node is inserted into the left subtree of the right child, which disturbs the balance factor of an ancestor node, making it right heavy. So how do we fix the problem? Perform a right rotation on the right child followed by the left rotation on the node. So another slide. It's a very important topic is, what is the application of AVL tree? AVL tree is used as a first example self-balancing binary search tree in teaching DSA, as it is easier to understand and implement compared to red black tree. Very important point is implementation of the AVL tree as compared to red black tree is easy. Application and other, where insertion and deletions are less common but frequent data lookups along with other operation of BST like sorted, traversal, floor, cell, man and max. Red black tree is more commonly implemented in language library like map in C++, set in C++, tree map in Java, and tree set in Java. AVL tree can be used in a real-time environment where predictable and consistent performance is. So these are the application of